Hi class, in this section we're going to take a look at polygons, section 9.2 of our textbook. So first of all, polygon is defined, well, we've got a plane figure is closed. We've got to start here before we talk about polygons. Closed figure if we can draw it without lifting a pencil, and the starting and end points are the same. A plane figure is simple if we can draw it without lifting the pencil, and in drawing it we never pass through the same point twice. Possible exception of the starting and ending points. So let's take a look at a couple of these. Let's draw them with my pen. So if I start here and I go around and trace the shape, did a bad job there apparently, but that is closed and it's simple because I didn't have to lift up my pen. So if I shade or trace this shape, I didn't actually come back. So it's simple. I didn't have to pick up my pencil, but it's not closed. Here I can start, but I have to cross over the same place twice, and so it is closed, but it's not simple. And last here, this one is not simple, and it's not closed. In other words, I cross, and it doesn't go back together. Okay. So now a polygon. We've got a simple polygon. Polygon, is a simple closed plane figure consisting only of line segments called edges, and such that no two consecutive edges lie on the same line. We call an endpoint of an edge a vertex, and plural is vertices. Polygon is regular if all of its edges are the same length and all of its angles have the same measure. So let's talk about some shapes here. So this is not closed, therefore it is a non-polygon. This one is not simple and is not closed, still not a polygon. This is a circle, but it's not a polygon. Polygon has line segments. A circle is not a line segment. Here are some polygons. So these are simple and they are closed. Okay. Here are some more polygons. These are simple and closed. Now notice the next part. Non-regular and regular. So regular means that the sides are the same length and the angles have the same measure. In other words, if I went in here, these are all 90-degree angles. They are all having the same measure. We'll talk about define what these angles are, but they are all the same also. We'll be figuring out what that part is later. Notice these ones, these line segments are different. The angles are all over the place, so they're non-regular. So regular means everything is the same. So here is a list of names for polygons. Maybe you've heard them before. Of course, triangle, quadrilateral, pentagon, hexagon, 6 sides, heptagon, hepta meaning 7, octa, octopus has got 8, nonagon, that's a weird one, 9, non, deca is 10. Okay, we'll be seeing some of those. So polygon is convex. Here's another definition. Convex, if any 2 points, x and y, so here's our points x and y, if they're inside the polygon, the entire line segment xy also lies inside the polygon. It probably doesn't make enough sense to look at the shape this way as much as it is to look at one that's not convex. So what it means is if you have any place where the angle bends in and I can actually draw a line across like this, but on the inside, then it's non-convex. Anytime that I can go to all the angles and put a line like that on them, it's a convex shape. Okay, so this is a convex angle, but this is our concave. It falls in, so it's non-convex, concave. It falls in. Now we got to talk about triangles. Well, we've got triangles have 3 sides, obviously, but there's 2 types of triangles. There's isosceles triangles and there's scalene triangles. You're probably thinking, well, there's a lot more triangles than that. There's right triangles and there's obtuse triangles. I know, but specifically there's just 2 types. I'm talking about the sides. The angles are different. You heard me say obtuse and right. But here, just talking about their sides, there's two types. There's isosceles and scalene. Scalene means no sides are equal. These are all different measures. And isosceles is at least 2 of the sides are equal. You could have all 3 be equal, and it's technically still isosceles. So if I had a triangle that looked like this, if I could draw a perfect triangle where all the sides are the same, by the way, when you mark them like that, they mean they're the same. That's still isosceles. It's also regular. Equilateral is the other way to say that. All sides are equal, although my shape kind of squished when I copied on the PowerPoint. But all these sides are equal, and that is a special type of isosceles. It's also known as a regular triangle. which is weird because you would think that they're all regular triangles. But this one's regular because it's defined special as the word regular. Now let's talk about quadrilaterals. Well, quadrilateral, it specifically means quad. If you've ridden a quad, you know that it has 4 tires. Quadrilateral, lateral is a side, so 4 sides. Well, that means a lot here, so let's talk about the first type, 4 sides. Our most basic quadrilateral is a trapezoid, and that has at least 1 pair of parallel sides. Okay? So in other words, I could have drawn a shape that looked like this. I was having a hard time actually drawing one that wasn't having any parallel. So this is just a 4-side, this is a quadrilateral. Okay? And then our first regular type, or first special type, is a trapezoid. So at least 1 pair has parallel sides. Now here is a parallelogram where there are 2 pairs of parallel sides. And technically, this is a trapezoid. Trapezoid is here. A parallelogram is a trapezoid. Right, that way it's a little more sense. Now a parallelogram, hopefully you followed my arrow there. Sorry. Parallelogram comes over here, and from parallelogram we have 2 special types. We have a, oops, sorry, got a little excited with my animation there. 2 special types of parallelograms. So both of these shapes are parallelograms. This is a, which you've seen before, as a rectangle, and what you see down here is a rhombus. Now, rhombus is special because all sides are equal in length, and the rectangle is special because it has 4 right angles. But follow this, a rectangle is a parallelogram, a rectangle is a trapezoid. A rhombus is also a parallelogram, and it's also a trapezoid. So it's just special ways of talking about it. And finally, a square. Most of my students are very upset when I tell them a square is a rectangle. A square is a parallelogram. A square is a rhombus. A square is a trapezoid. So when you've been telling your kids, this is a trapezoid, that's not a square, it's actually wrong. A square is a trapezoid. It's all of these. A square is a special, it's a regular rectangle. So it's hard, but it's hard to mess with our definitions that we've learned growing up. But a square is just the most special type of quadrilateral. It is also a rhombus. Here's the definition of rhombus, and it fits that. Here's the definition of trapezoid. It fits that, so it is also a trapezoid. So hopefully that made you happy or made you upset. I don't know. Think about it, and it'll probably make more sense. Sum of interior angles of a triangle. I'm going to show you 2 different ways of looking at this, but there's a special property about what all the angles inside of a triangle add up to. If I cut these out, just cut it just like that, and lined them up, put them next to each other, there's A, there's B, there's C. If you slid those together, which I couldn't get my animation to do properly, sorry, and I actually drew my arc across there, made this a straight line. If I actually brought these all together, it looks like 180 degrees. It is 180 degrees, and if you actually took and cut a piece of paper or cut a triangle up and put them next to each other, it would add up to exactly a perfect line, a straight angle, which is 180 degrees. Another way of looking at this is from our parallel lines cut by a transversal. Okay? Now, if you extend these lines a little bit, you'll see that it is basically doing that same picture that I just made down here, but it's taking angle 1 and noting it has to be the same as angle 4. Angle 2 is still hanging out right there. And angle 3 has to be the same as angle 5. So it's basically just doing the picture that I just told you about right here. And it's showing you that this adds up to 180 degrees that way. So either way, sum of an interior angles of a triangle add up to 180 degrees. No matter what they are, even if they're all different, it will always add up to 180 degrees if I add angle A plus B plus C. It'll give me 180 degrees. And that's important because it's going to help us find other shapes. So for example, here's a pentagon. I thought I had the regular pentagon without it, but apparently I don't. But if I had well, let's just draw a special regular pentagon off to the side. You'll see that I built that. So if I just draw a line across a pentagon, and then draw another line across the pentagon, I've got pretty much what's happening over here. There's 5 sides, and what you'll see is that there's 1, 2, 3 triangles. Well, if I want to know how much the angles inside of a pentagon add up to, all I have to know is that this is 180 degrees here, this is 180 degrees here, and this is 180 degrees. So when there's 5 sides, we get 3 triangles, and so it's just 3 times 180 degrees, which means that I have a total, 180 times 3, of 540 degrees inside of a pentagon. So inside of a pentagon, there's 540 degrees. And a very similar thing can be done here. If I just make a triangle by cutting it in half, you'll see that I have 2 triangles, and then that makes 2 times 180 degrees. Because this triangle has 180 degrees, this triangle has 180 degrees, and if I add that up, I get 360 degrees. So I know that you're thinking circles 360 degrees, but inside of a quadrilateral, if I add angle C plus angle B plus angle A plus angle D, if I add those up, A plus B plus C plus D, it would give me 360 total degrees. Now, be careful not to cut this up too much if you're trying to do this on your own on a different shape and you cut it up this way. Oops, sorry. You don't get 4 triangles. What you'd have to do is you'd have this shape in the middle where there's angles over here that you're counting into your overall total, so it would really mess things up. You don't want an extra angle on the inside. That's why I noticed both shapes so far, I only had, I only cut it in a way that if I cross as many vertices as I can without making a double shape. So if I go back to this one, notice I didn't draw like one right there because I'd have to cross one of the triangles I had already. Okay. So the pattern, there is one, is that in a triangle there's 3 sides, and that's 180 degrees. In a quadrilateral, there's 360 degrees. In a pentagon, it's 540 degrees. Here's the pattern. It's 1, 180 degrees. It's 2, 180 degrees. It's 3, 180 degrees. The pattern is this theorem. Angle sum of a polygon is n minus 2 times 180 degrees. In other words, how do I go from 3 to 1? I subtract 2. How do I go from 4 to 2? I subtract 2. How do I go from 5 to 3? I subtract 2. So if I want a pentagon, or sorry, pentagon, I meant to say decagon, 10-sided shape, if I want to know what it adds up to, I take 10 minus 2 and times it by 180 degrees. So inside of a decagon, it's 8 times 180 degrees is 1,440 degrees inside of a decagon. And we'll work on that a little bit more in these subsequent problems. But here's another special tool, and that is that if I want to know on a regular polygon what the interior angle is, so in other words, if I go back to that decagon that I had, the 1,400, so if I have a decagon, if it's regular, in other words, all the sides are the same, I take my 1,440 and divide it by how many angles there are, which is 10. Sides, angles, same amount of angles as sides. So if I divide that by 10, each angle has 144 degrees. Oops, that was supposed to be a degree symbol. So in a triangle, let's go back to a triangle, it might make more sense. In a triangle, if I have a regular one where all the sides are the same, that means all the angles are the same. Well, in order for them to all be the same, I take 180 divided by 3, and they would be exactly the same if they were all 60 degrees. So if I had 60, 60, and 60, they are all the same angles. Okay. So if I have similar shapes, 2 polygons are similar if their corresponding sides are proportional and their corresponding angles are proportional. So here are 2 similar shapes, shape A, shape B, and these are 1, 2, 3, 4, 5. They're both pentagons. They're not they're concave. They're not convex. But these sides are corresponding. Notice how they have an angle here in common. All their angles will match up. So this angle would match up with this angle. I could mark 2 marks here. You would see those are the same. Everything corresponds in them. So this side corresponds with this side, and so on. Now, why that's helpful is because we can make proportions. So what we've got here is a shape across, you're trying to build a bridge across this lake. I think, I don't have the words for it, but the job is that you've got this distance across the lake and we want to build a bridge. So how long of a span is this bridge going to have? If you have this similar shape down over here, the similar triangle, what we notice is that these angles are vertical, so this angle matches up with this guy. And this 6 here would match up with this D right here. It's not that they're the same, but that they are proportion. So 8 has a proportion with 20. So what that means is I can actually set up a great ratio with corresponding parts and put them over top of each other. So 8 is as to 20 as 6 is to D. And I didn't make it very nice for myself. It'd be a lot easier to solve if I wrote it the other way and wrote that 20 is as to 8 as D is to 6. That way it's a lot easier to solve. You can just flip these over, by the way. I'd show you in person, but I can't flip my hand and show you how it flips, but I'll draw an arrow squiggly. If I flip both of these over, it's the same thing. But so I'm establishing big triangle over small triangle side, big triangle side over small triangle side, so that I get an easy to solve problem. So I'll know how far across this bridge is because of my ratio if I just multiply. I was trying to get a different color and I've got a highlighter. If I just multiply 6, sorry, come on, there we go, multiply 6 to both sides, and then take out my calculator, D is equal to 20 times 6 divided by 8. So if I just do that on my calculator, 20 times 8 divided by 6 gives me distance across is 26.67 feet or meters or whatever it was in this original, feet, I'm sorry, it's actually there. So 26.67 feet is how far it is across based on my proportion that I set up. Okay, so here we have a problem that's very similar to one that you have in your assignments where your job is to find angle A. That's this guy right here. Well, how do I do that? I don't have any numbers in here. Well, actually, there are numbers. There's quite a few. But the point is that we have to remember that this all adds up to 180 degrees. If I take 2x minus 5 and add it to x plus 20 and add that to x plus 5, the whole thing should add up to 180 degrees. So notice this is my first, second, and third angles. I want to add them up together. So my job is to do like terms. So if I just combine my like terms, I'll see that I have 2 x's, another x, and a fourth x for a total of 4 x's. And then I have, so that was 2x, x, my x there. And then I combine my negative 5 with 20, and that should give me 15. And then I add 5 to it, and I get 20 again, so it's 4x plus 20 equals 180 degrees. Kind of running out of room there, so I'll write it up top. Sorry, 4x plus 20 equals 180 degrees. And so to finish solving, I subtract my 20 from both sides. And I get 4x equals 160. Divide by 4 to finish. And x is equal to 40. Now, 40 is not your answer. Don't type that into the lab as your answer because here it's x plus 5. X equals 40, but a is 40 plus 5. So my actual answer for a is 45 degrees. So again, x is 40, but I have to add 5 to it to get my 45. Okay. Now we've got another similar pond problem with what you've got. This is actually very similar to what you have in your assignments. And what you want to look at here is your distance across the pond is there's 2 similar triangles here. It's hard to see because you got the one triangle inside the other. Let me break it apart for you. So you got this triangle here where you've got the pond distance. That's what we're looking for. And you've got a total here of 195 plus 65 to get the total distance there. It doesn't tell us the total distance here. It just tells us that from here to here is 195, and then there's an extra 65 there. And then you've got your extra small triangle where they tell you this is 65 and this is 40. So the job is to set up a ratio. And like I did before, I'm going to say big triangle part over little triangle part that matches up. So what I'm noticing is that the 40 is in the same location as the P. And then I go ahead and add this together. 195 and my 65 gives me 260. So what that means is my big triangle part of 260 corresponds to my 45, so I put it over top, or 65, sorry, put it over top of your 65, and now I have big triangle over little triangle parts, corresponding parts, is what I've got set up here. So P over 40 and 260 over 65. So if I set it up this way, I put my corresponding parts over top of each other, it allows me to solve for a missing part. So if I multiply 40 to both sides, it allows me to get the answer for P. So P is going to be equal to 260 times, or divided by 65 times 40. And then you just type that into your calculator and you'll know what P is. So I take 260 divided by 65, and that gave me 4. So 4 times 40 gives me 160. So the distance across this pond is 160 feet. It's supposed to be a T. All right. And that's it for this section. If you have any questions, please ask me through the Ask My Instructor feature of the lab.